Welcome everybody to now the third event of our PhD seminar series, and today it's a great pleasure for me to welcome Marc Yor from the University of Paris, who is one of the world leaders in aspects on Brownian motion, and will speak today on certain aspects of Brownian motions. As I understand, it will be on quadratic functionals today, so that's it's particularly interesting for those who are working in econometrics. And feel free to interrupt Marc whenever you have a question or when you feel we are progressing too fast, maybe. Okay, I leave it to Marc now.
Okay, thank you very much. So it's very interesting and fascinating to be speaking here. I was really impressed by Rod's talk because many times I think we scientists have the impression that we are working in some corner of science, other people are working in other corners, and there is very little communication. It is sad, and many times we say, well, this has been done, or actually we don't even know it has been done. And what we have seen during the previous hour was really that Rod has been doing a lot of reading of the probabilistic works around Brownian motion, and he is trying to really use most of this reading for econometrics purposes, and I think this is very, very good. I wish I would have done similar work in the other direction, but maybe my lecture will help in starting this kind of program. Anyway, I feel it's very rewarding to attend this little sequence of sessions. So, in a kind of a sequel to Rod's lecture, I would like to give some of mine, but also of other people's presentations and aspects on especially quadratic functionals of Brownian motion. And first I will start on discussing why quadratic functionals. So, okay, so this is really the topic of today's talk, quadratic functionals of Brownian motion. So really I will try also to focus on things which are related to the Dickey-Fuller distribution. I mean, not too close, but not so far, and also on other aspects. So first of all, why or how can we get interested and how can we access quadratic functionals of Brownian motion? So there is maybe a theoretical starting point, okay, which I think that quadratic functionals of Brownian motion are at the second level of complexity. Level of complexity of what? Well, of the decomposition, or I should say Wiener chaos decomposition of a Brownian functional. So Wiener showed that if you take, okay, let us take Brownian motion indexed by 0, 1. This is not really important. I could take 0 infinity, but okay, let's work on time interval 0, 1 and take an element phi on L2 of the sigma field generated by Brownian motion up to time 1. Well, it is a well-known result by Norbert Wiener that you can decompose phi into the sequence of its chaos's components, okay? And by chaos's components, what Wiener means is, okay, there is the expectation of phi. Okay, and then there is an integral, a deterministic integral with respect to Brownian motion. Okay, so you have a certain function, a deterministic function phi 1 of u, and then double integral, integral 0 to 1 dbu, integral 0 to u dbv, and then I will write phi 2 of uv, plus etc, 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 and now you will have integral 0 to 1 dbu1, integral 0 to u1 dbu2, etc., integral 0 to un minus 1 dbun, and a deterministic function, again, phi n of u1, u2, un. So Wiener's idea is that somehow this should be thought of as a kind of a first order polynomial, second order polynomial, nth order polynomial of Brownian motion, or of Brownian increments. Okay? And you need these deterministic functions. And there is a Hilbert isomorphism between the L2, L2 space here and the L2 spaces where all these functions phi 1, phi n, etc. take place. And I simply write expectation of phi squared plus sigma n equals 1 to infinity, and then we find here the integral 0 to 1 dbu1, integral 0 to u1 dbu2 dot dot dot, integral 0 to un minus 1 dun phi n squared of u1 u2 un. Okay? Okay, so you have all these deterministic functions which are in L2 of their corresponding spaces. The series sums up and needs to be finite in order to define functional phi, which is square integrable and depends on the entire Brownian motion up to time 1. Okay, so when the functions vary, we call the spaces which are generated this way the chaoses. Okay, so you have the zeroth order chaos. So this is only constants. Okay, so we could even call this maybe little phi 0. So this is okay, phi 0 in R, and then C1. This is the space of these integrals. Integral 0 to 1 dbu phi 1 of u, where phi 1 is square integrable, and so on and so on. Okay, C2, okay, double integral 0 to 1 dbu 0 to u dbv, and phi 2 uv with square integrability, and so on. Okay, and then you may be interested in some generalized polynomial up to order n. Okay, so what I mean is that we could get interested in, say, okay, K2, and this will be what I will call the space of quadratic functionals. So K2 will be C0, that is R. Okay, direct sum with C1, direct sum with C2. Okay, so basically what I am saying is that we will get interested in a sum of three elements, a real, Gaussian integral, and double integral with respect to Brownian motion. Okay, and this I will call again the second chaos, or okay, so second, I don't know, integrated chaos, or anyway. So and the Dickey-Fuller quantity, of course, has a numerator and denominator which belong to K2. Why single out K2? Well, first of all, in C1 consists of only Gaussian variables. Okay, so integral 0 to 1 dbu phi of u, okay, is Gaussian, centered, Okay, so it's Gaussian, centered, and has variance equal to integral 0 to 1 du phi u squared. Okay, in fact, so of course you can have many different phi's which will give you the same distribution, but you know exactly how things are happening. It is not so clear with the second chaos, or any element of K2, but nonetheless we are able to really compute the laws of elements of K2, and essentially, although I am not going to give details about this, essentially this involves Sturm-Liouville equation. Okay, so second order differential equation, which can be also worked with Riccati equation. So you can go back and forth between Riccati and Sturm-Liouville. Okay, so K2, so the laws, okay, the laws of elements, okay, of K2 are accessible, let us say, okay, as soon at least as we have a Sturm-Liouville equation for which we can solve. Okay, we can solve explicitly. Okay, so already you see this is not so precise. But what I am going to focus on, especially in the second half of the talk, is that we could have two very different looking elements of K2 which have the same law. Okay, there are interesting. Let us say, coincidences, okay, which have not really been fully understood, but I will give already some explanation. So you could have an element, okay, so K and K prime belong to K2, and K equals in law K prime. Okay, so we will be interested. So some discussion of this. Okay, maybe before we get into this. Let's look again at Dickey Fuller quantity, or some related quantities, as Rod was discussing during the previous hour. So, okay, so let us look, for instance, at integral 0 to 1 du f of u bu squared. Okay, and I would like to convince you that we are really in K2. Okay, so you develop bu squared with Ito's formula, and so you get integral 0 to 1 du f of u, and now you get u plus twice integral 0 to u bs dbs. Okay, and so now you separate and you get a constant, so this is the element in C0, and then plus twice. Now you use Fubini, and you get integral 0 to 1 dbs bs, and integral from s to 1 of du f of u. Okay, and so you see here we are in C2. Okay, this is an element of C2, and this is an element of C0. Okay, so we are missing an element of C1 to be the most general case. Okay, so then there was a lot of discussion with Levy's area. Okay, and let me try to start on this again as an example, but a very important example. And also I will try to give some argument for the computation of the joint Laplace Fourier transform and so on. So maybe B, interest or some interest in Levy's area formula. Okay, so Levy gave some interpretation about the area quantity, okay, I should have 1/2, but associated with planar Brownian motion. Okay, so planar Brownian motion being here, zt equals xt plus I yt. As Rod was saying, it could start from a point different from 0, etc. I'm not going to look for the utmost generality, but so what happens is that, and this already explains some simplification in the formula. This may be written as a one-dimensional Brownian motion time changed with integral 0 to t ds xs squared plus ys squared. Okay, so where gamma, one-dimensional Brownian motion, is independent from xs squared plus ys squared as a process. Okay, so gamma is independent from the radial part of planar Brownian motion.
Mark, could you draw a picture of what that area geometrically is?
Yes, okay, so you have, I mean, it's the area of the curve which is obtained by following the Brownian curve, okay? You have the...
between the curve and the x?
Yes, yes, okay. Okay, as simply as this, but okay, or maybe we could say you approximate, so of course Brownian motion is not differentiable and so on, but you approximate by a polygon with finer and finer, and then you have the area and you pass to the limit, okay? Yeah, so this is one particular example of many line integrals along. So we could write like this also. Say integral x dy minus y dx along the Brownian path, and also for the winding number, for instance, same z 0t of omega x dy minus y dx over x squared plus y squared. So this is a very important aspect of Ito's integrals, especially with planar Brownian motion, which coincide with the line integrals which you may define along the Brownian trajectory. And this is very particular to the planar case because of conformal invariance of planar Brownian motion. Okay, but so I'm going to use this, or at least we are going to see how this comes into the discussion. And so amongst the different formulae which Rod was talking about, there is something like this. If we look at the characteristic function of at, then this is also the Laplace transform at lambda squared over 2 of the integral 0 to t ds xs squared plus ys squared. And this is really coming immediately from this independence of gamma and the radial part. Okay, so and there is an explicit expression which is 1 over cosh lambda, or rather lambda times t. And Levy was able also to extend this result to the so exponential I lambda at given zt equals little z, so given the final position at time t, and he obtained lambda t over shine lambda t exponential, and this is the term which Rod was saying is extremely difficult to manage, and this is absolutely correct. It's a nightmare, but it is there, and lambda t coth lambda t minus 1. Okay, so now of course so you see that now getting closer to Dickey-Fuller and so on. Oh, maybe here I should continue the discussion of the reduction to radial part, okay? Because in fact, again by rotational invariance, so just pushing this argument a little further, we get that this is exponential minus lambda squared over 2 integral 0 to t ds xs squared plus ys squared given xs squared, xt squared plus yt squared equals norm of z squared. Okay, or even, in fact, we could say given xt squared equals little x squared, yt squared equals little y squared. Okay, and now you see that somehow because of the independence of x and y, you can also rephrase this result into a purely one-dimensional Brownian motion result. Okay, just dividing by 2, so to speak. Okay, so okay, let me write it correctly. Integral 0 to t ds xs squared given xt equals little x equals, okay, so now we take the square root, okay, lambda t over shine lambda t to the 1/2 and then exponential minus x squared over 2t dot dot dot. Okay, so you see that, Levy was interested in computations involving the area, but somehow behind this computation, or closely linked with this computation, there is a result about one-dimensional Brownian motion, and in fact a result which is extremely related with the decay-Fuller quantity, okay, because it exactly brings in the integral of the square of Brownian motion and its value at time t. Maybe what I could do right now is to give some explanation or some way to obtain this formula, because I think Rod did not have time to go into this. There are a number of ways to do this, but it may be interesting to explain one of them, because this comes in many ways. Okay, so here, okay, it's not. Okay, so maybe I'm erasing the wrong things each time. Okay, well. Okay, so one possibility is to use absolute continuity relationships between Brownian motion and the Einstein-Uhlenbeck process. Okay, so a proof of Levy's formula, may be done by considering the absolute continuity relationship between the law of Einstein-Uhlenbeck process with parameter lambda and the law of Brownian motion. Again, as I explained, I can restrict my discussion to one-dimensional Brownian motion. Okay, so between p lambda and p0, where p lambda denotes the law of the Einstein-Uhlenbeck of the OU process with parameter lambda. Okay, so the Einstein-Uhlenbeck process is the solution of dxt equals lambda xt dt plus dwt. Okay, and x0 equals little x, or I will take 0 today or now. And of course, so P0 corresponds to the case lambda equals 0, and this is pure Brownian motion. That relationship is a very particular case of Girsanov theorem, and it can be stated as follows. So P lambda now I am considering p lambda and p0 on a canonical path space, that is the space of continuous functions from 0 infinity to r, and xt is my canonical process. It's the process of coordinates, and ft is the filtration of the past of my canonical process x up to time t, say. Okay, so x, there is only one process, that's the canonical process and path space, but there are different different distributions. Okay. Okay. So what Girsanov's theorem tells us in this very particular case is that this is exponential of lambda integral 0 to t xs dxs minus lambda squared over 2 integral 0 to t xs squared ds. Okay? And this is the density, this is a martingale density with respect to Wiener measure, to the law of Brownian motion, which here I write as P0, again restricted on Ft. Okay? And now, again, we see that this is very well related or linked with our problem, because again we can get rid of the stochastic integral or rewrite it as we like. So that is lambda over 2 xt squared minus t minus lambda squared over 2 integral 0 to t x squared ds dot p0 and ft. Okay, and now from there, what we use, which is very particular, is that we know the semigroup of the Ornstein-Uhlenbeck process, because the Ornstein-Uhlenbeck process is a Markov process, which is also a Gaussian process, and so it is very easy to compute its semigroup, which in general is very difficult. So what one does from here is that one looks at E lambda of, let us say, f of xt, okay, for a generic function f, okay, and then we apply this formula. So we have E0 of f of xt and exponential, etc., etc. Okay. So now what I say is that, well, this only involves the semigroup of xt under p lambda. So this is integral of dx p lambda t 0x f of x. And on the right hand side, this is also integral dx p0 t 0x f of x. And now I am going to condition this with respect to xt equals little x, okay? So what I am getting is, excuse me, exponential of lambda over 2 little x squared minus t minus lambda squared over 2, or maybe at this point I could write expectation of e to the minus lambda squared over 2 integral 0 to t x squared ds given xt equals little x. Okay. Now this equality holds for every test function little f. Okay, and so this implies that we now have an expression of this conditional Laplace transform in terms of the ratio of the two semigroups. But we know these semigroups. Okay. So what we get is that E0 of e to the minus lambda squared over 2 integral 0 to t x squared ds given xt equals little x equals, okay? So we get p lambda t of 0x divided by p0t of 0x, and then there is this term also, which I bring to the left-hand side, so it gives me exponential minus lambda over 2 x squared minus t. Okay? And again, as I said, we know P lambda very well. In fact, this goes back to Doob. Okay, this is one of maybe the first result on stochastic processes written from stochastic integrals. I mean, anyway, the beginning, Doob was one of the first persons who used Ito's stochastic calculus, and from this equation he says that, well, I can solve this linear equation. This is e to the lambda t integral 0 to t e to the minus lambda s dws, okay? And now I write this as e to the lambda t, and a new Brownian motion time changed with the integral 0 to t e to the minus 2 lambda s ds. Okay, so I'm just going to write it like this, e to the minus 2 lambda s ds, okay? And so you see that you know the law of xt. It is a Gaussian variable, and you can it is centered here in this case, and you can compute its variance. This gives us p lambda, and we obtain Levy's formula in this way. Okay. Now I want to continue my lecture by this question about coincidences. Okay, and this what I call coincidences is different ways where are different situations or quantities which will bring us to the same results. And each time you see this, a priori you are a little astonished, and you really want to understand why two such functionals, k and k prime in K2, okay, have the same distribution. Okay, I do not claim I have a complete understanding of the situation. This would be a lie. But I think most of the cases which have occurred, in particular from physics, I think that we have some sound understanding. I would like to develop this aspect. But before really getting into this, there are several instances. And I want to discuss the first one, which has been very well recognized within the probabilistic community. Okay, and this is maybe point little c, understanding some coincidences. Okay, so some, well, maybe it would be more correct to say equalities in law. Okay, via Brownian local times. Okay, via Brownian local times, and what is called the Raynight theorems and Raynight theorems. Okay, so the story, as far as I told you, or the type of questions which Rod has been looking at and so on, are time questions. Okay, questions involving processes indexed by time. Okay, but in fact, the same kind of quantities occur also, or may be seen, in terms of the space or some space features of often the same processes. I mean, so space features of, let us say, Brownian motion for simplicity. Okay, so I want to be more precise. Okay, so space features of Brownian motion. Okay, so what could we call a space feature? That is, how does Brownian motion spends its time in, let us say, a certain set of the real line, or of the complex plane, and so on. Okay. Now, to discuss this, there are some processes which really take care of the visits of Brownian motion to different levels, okay? And these are the so-called Brownian local times. so Brownian local times, indexed. So they are indexed by both by time and by space, okay, by the level at which one looks. So let me explain about this. If we consider, so now this is a one-dimensional discussion. If we consider the following random measure, okay, so by random measure I mean the time which Brownian motion up to time little t has spent in a set, okay, in a Borel set in R. So this random measure, so I have fixed omega, almost surely for almost every omega is absolutely continuous with respect to Lebesgue measure. So in fact you can write it as an integral from minus infinity to infinity dx, indicator gamma of x, and there is a certain density, hadron-Nikodym density, which I will write as Lxt of omega. And these processes, Lxt of omega, which may be chosen continuous in x and t, okay, are the so-called Brownian local times. Let me explain or justify this terminology. This notion of Brownian local times goes back to Paul Levy, who was looking in particular at the value x equals 0. Okay, so if we admit, if we accept this identity, then by monotone class theorem, this is also true when I replace the indicator of gamma by any function. Okay, so ds f any Borel function, f of bs of omega is also okay, integral dx f of x and Lxt of omega. Okay, so this is so for every f, let us say from R into R plus. Okay, so I want, for the moment, I want to justify this term of local time. So let us consider a certain level, A. Okay, so let us fix A and consider maybe A plus epsilon and A minus epsilon. So we have this little band here, and time goes up to little t, and we are interested at the time which Brownian motion has been spending between A minus epsilon and A plus epsilon. So we take this with this gamma, okay, gamma being A minus epsilon, A plus epsilon. We divide by the width of this band, that is 2 epsilon. So what we get from here is that the limit as epsilon goes to 0, 1 over 2 epsilon, integral 0 to t, ds, indicator absolute value of bs minus a, smaller than epsilon. This is equal to, so here we have the integral from a minus epsilon to a plus epsilon. We divide by 2 epsilon, we let epsilon go to 0, and by the continuity, which I am assuming, we get that this is LAT of omega. Okay? So you see that LAT of omega is a quantity which occurs when you look at the time spent in a neighborhood of A, okay, with this width, let us say 2 epsilon, and you normalize. It's the infinitesimal local time. So it's the infinitesimal time. Okay, if you just looked at, if you just take gamma the singleton, okay, little a, then you will get 0. So this indicator of Bs equals a here for Lebesgue measure in time, you will get 0. You will never see the local time this way. You have to look at the derivative, so to speak. Okay. Okay, so this is the local time, and now what is very beautiful is that there is many properties of Brownian motion somehow transfer many properties of Brownian motion in time transfer in space to the local times when you have fixed the time, not any time, but when you are considering some very particular stopping times. Okay, so I want to stop here, and we resume in 5 minutes. Okay.